Tonight, I want to talk to you about a prison. Not a prison made of bars, not a prison built by hands, but a prison made of physics, of mathematics, of the fundamental laws of the universe. A prison so vast that it encompasses entire galaxies, so absolute that no technology can escape it, so permanent that it will last until the end of time. And we are all inside it. Every civilization, every intelligent species in the entire universe, trapped, isolated, separated, by distances so vast they defy comprehension, by energy requirements so massive that interstellar travel is nearly impossible, by cosmic speed limits that no engineering can overcome. This is why aliens cannot reach Earth. Not because they don't exist. Statistically, they probably do. Not because they aren't intelligent enough. They could be far more advanced than us. But because physics won't allow it. Because the universe itself is a barrier, insurmountable, absolute. Tonight, for the next 4 hours and 20 minutes, I want to take you on a profound journey through every barrier, every obstacle, every limitation that makes interstellar travel nearly impossible. First, distance, the incomprehensible scales that separate the stars. Second, energy, the massive requirements to reach significant speeds. Third, the rocket equation, the tyranny of mass and fuel. Fourth, time, the centuries, millennia that interstellar travel requires. Fifth, detection, why Earth is invisible even from nearby stars. Sixth, physical dangers, radiation, impacts, entropy. Seventh, the limitations of advanced civilizations. Why even a Type 3 civilization cannot overcome these barriers. And eighth, the speculations, wormholes, warp drives, and why they are probably impossible. In the end, you will understand why the universe is so silent, not because we are alone, but because everyone is trapped in their own star systems, their own regions of space, looking at the stars, wondering, like us, but unable to reach, unable to connect, because physics won't allow it. And maybe that's the loneliest thing of all. Not that we are alone, but that we are not alone, that there are others, billions of others, but separated forever by the incomprehensible void, with no hope of contact, no possibility of encounter, each one crying out into the void, unheard. So let's begin with the most basic thing, with the illusion that deceives us every night, when we look up at the sky and see the stars and think they look so close, but they're not. Chapter 1. The illusion of proximity, the night sky. Lies look up on a clear night, far from the city lights, and you'll see stars, thousands of them, bright points of light, some bright, some dim, some clustered together, some alone. And they all seem reachable, somehow. But that's the biggest illusion of all, because the night sky lies, not about the existence of the stars. They're there, real, but about the distance, about how far away they really are. When you see two stars together in the sky, your brain assumes they're close, right next to each other, but they could be hundreds of light years apart, one close, the other infinitely far away, just aligned, from our perspective, by chance. It's like looking at two planes in the sky. One could be 5 kilometers away, the other 10 kilometers. But from the ground, they appear to be on the same side. The sky is a two-dimensional projection of a three-dimensional space, and it flattens everything. It hides the true scale, and the true scale is incomprehensible. Let's use an example. The closest star, Alpha Centauri, actually Proxima Centauri, its companion, 4.24 light-years away. 4.24 light-years. What does that mean? It means that light, traveling at 300,000 kilometers per second, takes 4.24 years to travel from that star to here. So how many kilometers? 1 light year is approximately 9.46 trillion kilometers. So 4.24 light years is approximately 40 trillion kilometers. 40 billion kilometers. 40 trillion. Your brain cannot comprehend that number. My brain cannot comprehend that number. No human brain can. We did not evolve for that. We evolved to comprehend distances of meters, kilometers, maybe hundreds of kilometers, not trillions. So we need analogies, scales, comparisons. Here's one. If you were traveling at 100 kilometers per hour, highway speed, it would take you approximately 45 million years to reach Proxima Centauri. 45 million years. Another, if you could count, one number per second, without stopping, counting to 40 trillion. It would take you 1.26 million years, over a million years, just to count. And that's the closest star, the closest neighbor, practically in our cosmic backyard. The next closest star, Barnard's star, is 6 light-years away. Then Wolf 359, 7.8 light-years away. Sirius, the brightest star in the night sky, is 8.6 light-years away. And most of the stars you see with the naked eye, they're hundreds of light-years away, some thousands. Betelgeuse, 650 light-years. Deneb, 2,600 light-years, and those are just stars in our galactic neighborhood. The Milky Way is 100,000 light-years across. The nearest galaxy, Andromeda, is 2.5 million light-years away. So when you look up at the night sky, and the stars seem close, reachable. Remember, it's an illusion, a comforting lie. The truth is, they are incomprehensibly far away, separated by voids that defy imagination. Chapter 2. Voyager 1. Our fastest object, our slowest progress. So how fast can we travel? Well, the fastest object ever created by humans is Voyager 1, launched in 1977, now in interstellar space, traveling at approximately 17 kilometers per second relative to the Sun, approximately 61,000 kilometers per hour. That sounds fast, and it is. By Earth standards, you could cross the United States in about 4 minutes, circumnavigate the globe in about 40 minutes. Impressive. But let's put that into stellar perspective. At that speed, how long would it take Voyager 1 to reach Proxima Centauri? Approximately 73,000 years. 73,000 years. For context, human civilization since the first cities is approximately 12,000 years old. All of written history, approximately 5,000 years. So Voyager 1, our fastest object, would take 73,000 years, 6 times all of documented human history, just to reach the nearest star. And Voyager 1 is constantly accelerating. No, it's in free fall, no propulsion, no additional acceleration, just the speed it gained from planetary flybys. If you wanted to get there faster, you need more speed, much more speed. And that requires energy, massive, incomprehensible energy. Chapter 3. The kinetic energy equation, the tyranny of speed. Kinetic energy, the energy of motion. It's calculated with a simple formula. E equals 1/2 mv squared, where m is mass, and v is velocity. And note velocity is squared. That means doubling the speed requires 4 times the energy. Tripling the speed requires 9 times the energy. 10 times the speed requires 100 times the energy. It's not linear, it's exponential, and that's a massive problem for interstellar travel. So let's do some math. Suppose you want to send a small probe to Proxima Centauri. Mass, 1,000 kilograms, about the size of a small car. Target speed, 10% of the speed of light, 30,000 kilometers per second. At that speed, you would reach Proxima Centauri in about 42 years, within a human lifetime. Doable, maybe. But how much energy does it require? E equals 1/2 times 1,000 kilograms times open parenthesis 30 million meters per second, close parenthesis squared. E equals 1/2 times 1,000 times 900 trillion E equals 4.5 times 10 to the 20 power joules. What does that mean? Well, a large nuclear power plant generates approximately 1 gigawatt. That's 10 to the power of 9 watts, or 10 to the power of 9 joules per second. So, to generate 4.5 times 10 to the 20 power joules, a nuclear power plant would have to run for approximately 4.5 times 10 to the 11 power seconds. That's about 14,000 years. 14,000 years of nuclear power plant production to accelerate a 1,000 kilogram probe to 10% of the speed of light. Or, in more understandable terms, that's roughly the total energy produced by all of human civilization in about 1 year. All the electricity, all the oil, all the gas, all the coal for a whole year for a single probe to a single star. And that's just to accelerate. You also need to decelerate when you arrive, which requires the same amount of energy. Again, so double that. 28,000 years of nuclear power plant production, or 2 years of global energy production. And if you want to go faster, say 20% of the speed of light, the energy quadruples, because speed is squared. 50% of the speed of light, 25 times more energy. 90% of the speed of light, 81 times more energy. You see the problem. Every increase in speed requires massive increases in energy, and eventually you reach physical limits, and economic ones, where you simply can't generate that much energy, no matter how advanced your civilization is. Chapter 4. The Rocket, Equation, the Tyranny of Mass. But wait, there's more, because until now I've been assuming that you're only accelerating the probe. But how do you accelerate it? With a rocket, with propulsion. And that requires fuel, fuel that has mass. And here's the problem. The mass of the fuel adds to the total mass, which also needs to be accelerated, which requires more fuel, which adds more mass, which requires even more fuel. It's a vicious circle called the tyranny of the rocket equation, and it's described by Tsiolkovsky's equation. Delta V equals VE times natural log of m0 over mf, where delta V is the change in velocity, VE is the escape velocity of the rocket, m sub 0 is the initial mass, spacecraft plus fuel, m sub f is the final mass, spacecraft only, and ln is the natural logarithm, which means that the relationship is logarithmic, not linear. To reach high speeds, you need massive mass ratios. M sub 0 over M sub f needs to be huge, so let's calculate. For chemical propulsion, traditional rockets, the escape velocity is approximately 4,500 meters per second. To reach 10% of the speed of light, 30 million meters per second, you would need a mass ratio of M sub 0 over M sub f equals E to the power of 30 million over 4,500, approximately equals E to the power of 6,667. What is E to the power of 6,667? It's a number with approximately 2,895 digits, incomprehensibly large. To put that in perspective, if your ship weighs 1,000 kilograms, the fuel needed would weigh more than the observable universe. That's no exaggeration. Literally more mass than all the galaxies combined. Obviously impossible, so chemical rockets don't work. For interstellar travel, they simply can't reach the necessary speeds. The rocket equation prohibits it. Chapter 5. Advanced Propulsion, Fusion, Antimatter, and Their Limits. So what about advanced propulsion, nuclear fusion, antimatter, better technologies? Nuclear fusion. Fusion releases much more energy than chemical combustion, and the escape velocity of a fusion rocket could be approximately 10,000 to 30,000 kilometers per second. Much better than chemical rockets. But it's still not enough to reach 10% of the speed of light with fusion. You would still need mass ratios of 10 to 1 or more. That means 10 kilograms of fuel for every 1 kilogram of spacecraft. Feasible? Perhaps, but incredibly challenging. And we haven't yet achieved sustained fusion on Earth, much less in a compact rocket. In space, it's technology of the future, maybe within decades, maybe never. Antimatter. Antimatter is the perfect propellant. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into energy. E equals mc squared. Perfect efficiency. With antimatter, relativistic speeds become possible. 50%, 90%, even 99% of the speed of light, within the realm of physics. But there's one massive problem: production. Antimatter does not exist naturally. In significant quantities, you have to make it in particle accelerators, and it's incredibly inefficient. Currently, producing 1 gram of antimatter would cost approximately $25 trillion. 25 trillion for 1 gram, and for interstellar travel, you would need tons. The cost would be astronomical, literally, more than the world's GDP for centuries. And then there's storage. Antimatter annihilates on contact with normal matter, so you need magnetic containment, perfect, faultless, for decades during the journey. One single failure, massive explosion, mission over. So antimatter is theoretically possible, but practically almost impossible, at least with foreseeable technology. Chapter 6. Relativistic effects. The speed of light as an absolute limit. And then there's the ultimate limit, the speed of light. C. Approximately 300,000 kilometers per second. According to Einstein's special relativity, nothing with mass can reach the speed of light. No matter how much energy you use, it's a physical limit. Absolute, insurmountable. Why? Because as you approach the speed of light, your effective mass increases. From the perspective of a stationary observer, at 90% of the speed of light, your mass is approximately 2.3 times your rest mass. At 99%, approximately 7 times. At 99.9%, approximately 22 times. At 99.99%, approximately 71 times. And as mass increases, more energy is required to accelerate, exponentially more. Asymptotically approaching infinity. To reach exactly the speed of light, it would require infinite energy, which is obviously impossible. So the speed of light is a cosmic speed limit, built into the fabric of space-time. No technology can overcome it, no engineering. It's not an engineering problem, it's fundamental physics. Chapter 7. Time. Generations in the void. So even with advanced technology, interstellar travel takes decades, centuries, millennia, depending on the distance and the speed. And that introduces the problem of time. How do humans or any living beings survive for so long? Option 1. Generational ships. Ships large enough to support a population. That lives, reproduces, dies during the journey. Generations born in space, who never know Earth, eventually arriving at their destination, centuries after launch. But generational ships have massive problems. First, size. To support a viable population, say 500 to 1,000 people, you need a huge ship. Habitats, farms, water and air recycling, manufacturing, repair, entertainment, education. And the bigger the ship, the more mass. More mass means more energy to accelerate, and we're back to the energy problem. Second, genetics. A population of 500 to 1,000 is small. Genetically, risk of inbreeding, genetic drift, loss of diversity. Over generations, the population could weaken, become sick. Third, social. Maintaining social cohesion for centuries in confinement, with limited resources, no escape, no new environment. There will be conflicts, factions, possibly violence, ideological fragmentation, loss of original purpose. Future generations could forget the mission or reject it. Fourth, technical. Systems fail over time, inevitably, and repairs require parts, experience, resources, which could run out during the journey, and entropy. The second law of thermodynamics. Everything degrades over time. Everything, ships included. So generational ships are theoretically possible, but practically incredibly challenging. And they have never been attempted, not even on a small scale. Option 2. Suspended animation. Freeze the crew. During the journey, wake them up upon arrival. But we don't have this technology. We have achieved cryogenics, freezing bodies after death, but not reviving them. That's science fiction for now, and there are problems. Ice crystal formation, cell damage, how to restart metabolism. The brain. Without damage, problems that could be unsolvable. Option 3. Artificial intelligence. Send machines, not humans. Autonomous probes that don't age, don't need food, can travel for centuries without biological problems. This is more feasible, and this is probably how we will explore, initially, with probes, like Voyager, but more advanced. But it doesn't solve the problem for humans if we want to travel, personally, to the stars. Time remains a massive barrier. Chapter 8. The Waiting Paradox. Technological obsolescence. And there is another paradox related to time, called the waiting paradox, or the problem of obsolescence. Suppose you launch a spacecraft today to Proxima Centauri, traveling at 10% of the speed of light. It will arrive in 42 years, but technology improves exponentially over time. In 20 years, you could have better engines, more efficient ones, that can reach 20% of the speed of light. So you launch a second spacecraft. In 20 years, it travels at 20% of the speed of light. It arrives in 21 years after its launch. But the first spacecraft, launched 20 years ago, still has 22 years of travel remaining. So the second spacecraft arrives first. It overtakes the first one. En route, do you see the problem? If you wait for better technology, you arrive faster. But if you don't wait, you'll be overtaken. So when do you launch? Now? Or do you wait for technological improvements? If you wait, how long? 10 years? 50 years? 100 years? There is no right answer. Because technology always improves. And there will always be faster ships in the future. So maybe you never launch, because it always makes sense to wait. But if you never launch, you never arrive. Paradox. Chapter 9. The invisibility of Earth, why they can't find us. And now let's change our perspective. Not us traveling to them, but them traveling to us. Why haven't aliens come to Earth? One reason, they don't know we're here because Earth is invisible. Even from relatively close distances, think about it. Searching for habitable planets around other stars. It's incredibly difficult. Even with our best telescopes, planets are small, faint, drowned out by starlight. Detecting them requires sophisticated techniques, transits, radial velocity, direct imaging. And we've discovered thousands of exoplanets. Yes, but almost all within a few thousand light years. And most are gas giants, or planets in close orbits. small, Earth-like planets. In habitable zones, they're much harder to detect, especially around faint stars, red dwarfs. And then there's the detection of life. Biosignatures, signs of biological activity. We look for oxygen, methane, ozone in exoplanetary atmospheres using spectroscopy, analyzing filtered starlight. But that requires massive telescopes, long observation time, and it only works for relatively nearby planets, within about 100 light years. Maybe. Beyond that, Earth is effectively invisible. You can't detect its atmosphere, its biosignatures. It's just too far away, too faint. Chapter 10. Radio signals, a 200 light-year bubble. But what about radio signals? We've been broadcasting since about 1900. Radio, television, radar. Signals traveling into space at the speed of light. And those signals form a bubble. Expanding at 300,000 kilometers per second around Earth. After 125 years, that bubble is about 125 light-years across, 250 light-years in diameter. And inside that bubble, any civilization with sensitive radio telescopes could detect our signals and know we're here. But here's the problem. 250 light-years is tiny. On a galactic scale, the Milky Way is 100,000 light-years in diameter. So our radio bubble covers approximately 250 over 100,000 cubed is approximately 0.000015, approximately 0.0015% of the volume of the galaxy. 1 in 65,000. Those are the odds that a random civilization is within our radio bubble and can detect us. And that assumes they have radio telescopes, that they are listening, that they recognize our signals as artificial, that they care about visiting us. So even with radio transmissions, Earth is almost invisible, almost undetectable to the vast majority of possible civilizations. Chapter 11. The inverse square law, signals that fade. And there's another problem with radio signals. They weaken with distance, according to the inverse square law. When a signal travels outward, it spreads out in all directions, spherically, and the intensity decreases with the square of the distance. If you double the distance, the intensity drops to 1/4. If you triple the distance, it drops to 1/9. If you increase it 10 times, it drops to 1/100th. So at 10 light-years, a signal is 100 times weaker. At 100 light-years, 10,000 times weaker. At 1,000 light-years, 1,000,000 times weaker. And eventually, the signal becomes indistinguishable from background noise. Cosmic background radiation, stellar interference, thermal noise. Even with massive antennas, sophisticated signal processing, beyond a certain distance you simply cannot detect the signal. It's there, but drowned out, lost. So our radio transmissions could be undetectable beyond a few hundred light-years, maybe 1,000 at best. Beyond that, we are silent, invisible, unknown. Chapter 12. The physical hazards, relativistic impacts. And now, let's talk about the dangers of interstellar travel, because space is not empty. There is dust, atoms, particles, and at relativistic speeds they are deadly. Interstellar space has about 1 atom of hydrogen per cubic centimetre. Not much, almost empty, but at 10% of the speed of light. Every atom of hydrogen becomes a high-energy projectile. Let's do the math. An atom of hydrogen has a mass of about 1.67 times 10 to the minus 27 kilograms. At 30,000 kilometers per second, 10% of c, it has kinetic energy. E equals 1/2 times 1.6, 7 times 10 to the minus 27 times 30 million squared. E is approximately 7.5 times 10 to the minus 13 joules. That doesn't sound like much, but it's enough to ionize atoms, break chemical bonds, cause damage at the atomic level. And it's not just one atom, it's trillions per second, hitting the ship constantly for years. It's like cosmic radiation, but more intense, eroding the hull, damaging electronics, breaking DNA, if there is a living crew. And then there are the dust particles, interstellar dust, grains of approximately 0.1 to 1 microns, rare, but present. A 1 microgram dust particle, at 10% of the speed of light, has kinetic energy of approximately 450 joules. That's roughly the energy of a rifle bullet, and it hits with that force, piercing the hull, creating a hole, explosive decompression, catastrophic damage. So you need armor, thick, heavy, layers of material, to absorb impacts, magnetic fields, to deflect charged particles. But that adds mass, which requires more energy. Back to the problem of mass and energy. And at higher speeds, 20%, 50% of C. The impacts are even worse, exponentially worse. So interstellar space is hostile, not a friendly vacuum, but a battlefield of invisible projectiles, constant erosion. Chapter 13, Entropy, Inevitable Degradation. And then there's entropy, the second law of thermodynamics, which says, in a closed system, disorder always increases, and a spacecraft is a closed system, isolated, no resupply, no external repair. And over time, things break, systems fail, components wear out, electronics degrade, materials fatigue, no matter how well you design, how redundant you make the systems. Eventually, entropy wins, and on a journey lasting decades, centuries, entropy is your enemy, slowly, inexorably, destroying your ship, so you need maintenance, repair. But that requires spare parts, tools, expertise, all of which have mass, limitations, and eventually you run out of parts. No repair capability, and the ship fails. Irrevocably. So entropy puts a time limit on how long a ship can function. Centuries, maybe, millennia, unlikely. And that limits how far you can go. Even with perfect technology, unlimited energy, entropy eventually stops you. Chapter 14, Advanced Civilizations, the Kardashev Scale. But what about advanced civilizations far more advanced than us, capable of things we can barely imagine? The Kardashev scale classifies civilizations by energy use. Type 1 uses all the energy available on its planet, approximately 10 to the power of 16 watts. For Earth, we are at approximately 0.7 on the scale. Not yet Type 1. Type 2 uses all the energy from its star, approximately 10 to the power of 26 watts. For a star like the Sun, requires megastructures, like Dyson spheres, capturing all the stellar output. Type 3 uses all the energy in its galaxy, approximately 10 to the power of 36 watts, incomprehensibly advanced. So could a Type 2 or 3 civilization overcome the barriers I've described? Short answer, not really. More energy helps. Yes. A Type 2 civilization could accelerate larger ships, faster. It could launch thousands of ships, exploring multiple systems, but they are still limited by the speed of light. They still face the rocket equation. They still need to deal with relativistic impacts. Entropy, time. More energy doesn't change physics. It doesn't make C any faster. It doesn't eliminate entropy. It just makes some things more feasible. Not easy. And a Type 3 civilization could colonize the galaxy over millions of years with self-replicating probes, patience, time. But that's different from traveling to Earth, specifically, intentionally. To do that, They would need to know we exist, to decide we're worth visiting, have the technology and resources for the journey, actually do it. And each of those steps is uncertain, unlikely, perhaps impossible. Chapter 15. Wormholes, the shortcut dream. But what about shortcuts, wormholes, bending space-time, creating tunnels between distant points? In theory, allowed by general relativity, mathematical solutions to Einstein's equations. But there are massive problems. First, stability. Wormholes in natural solutions are unstable. They collapse instantly, before anything can happen. To stabilize them, you need exotic matter with negative energy density, pushing space-time outward instead of inward. Does such matter exist? We don't know. Probably not. We've never observed it. We've never created it. It could be physically impossible. Second, creation. Even if exotic matter exists. How do you create a wormhole? It would require massive energy, manipulation of space-time, beyond any conceivable technology. Third, navigation. Even if you can create and stabilize a wormhole, how do you navigate through it? The interior could be chaotic, unpredictable, with tidal forces tearing you apart. So wormholes are theoretically possible. Maybe, if exotic matter exists, if you can create them, but practically, highly unlikely. Science fiction, not science. Chapter 16. Warp engines, contracting space. And then there are warp engines, popularized by Star Trek, but based on real physics. The idea, you don't move the ship through space, you move space around the ship, contracting space in front of you, expanding space behind, creating a warp bubble. And inside the bubble, the ship is stationary, relative to local space, so it doesn't violate relativity, but the space outside the bubble moves, faster than light, possibly, taking the ship with it. Mathematically, this is consistent with general relativity, the Alcubierre metric, proposed in 1994. But it has massive problems. First, exotic matter. Again, it requires negative energy density to contract space, without gravitational collapse, which probably doesn't exist. Second, energy. Initial calculations suggested that you would need the mass energy of Jupiter, converted entirely into negative energy, for a warp bubble the size of a ship. Subsequent refinements reduced that to only the mass of the Sun, or less, but still incomprehensibly large. Third, causality. Warp engines could violate causality, allowing time travel, paradoxes which physics probably prohibits. And fourth, event horizon. The front of the warp bubble could form an event horizon, like a black hole, preventing you from controlling the ship or stopping it. So warp engines are theoretically possible under extremely speculative conditions, but practically, almost certainly, impossible. Chapter 17. Reality. Physics wins. So after all that, after exploring every possibility, every technology, every shortcut, the conclusion is clear. Interstellar travel is possible, technically, with advanced technology, massive energy, unlimited time. You could send probes, maybe even generational ships, to nearby stars within decades or centuries. But it's incredibly difficult. It requires resources on a planetary scale, or stellar, technologies we don't have, maybe we never will, and patience that exceeds human lifetimes, maybe civilizations. And for extraterrestrial civilizations, the barriers are the same, no matter how advanced they are. Physics is universal. Distance, stars are incomprehensibly far apart. Energy, significant speeds require massive energy. Rocket equation, fuel mass scales exponentially. Time, journeys take decades, centuries, millennia. Detection, habitable planets are hard to find. Dangers, relativistic impacts, radiation, entropy. Speed limit, the speed of light is insurmountable. And shortcuts, wormholes, warp drives, require speculative physics, exotic matter, which probably doesn't exist. So the conclusion is, aliens cannot reach Earth. Not because they don't exist. They probably do. Not because they aren't advanced enough. Some could be far more advanced than us, but because physics doesn't allow it. The universe is a prison of distance, of energy, of time, and we're all trapped, permanently, in our own regions of space. Chapter 18. Cosmic Silence. Why no one visits. And this explains the cosmic silence, the Fermi paradox. Where is everybody? They're not here because they can't be here. They haven't visited us because they can't visit us. We don't receive signals because signals weaken. They get lost. And it's not that we're alone. There could be billions of civilizations in the galaxy, but all separated, isolated by the void, each looking at their stars, wondering, building radio telescopes, searching for signals, sending messages that no one receives because the universe is too big, and the speed of light is too slow, and the energy requirements are too high, so we remain alone, not philosophically, but practically, isolated by physics, by mathematics, by reality. Epilogue. Living in prison. So there you have it, the reason why aliens can't reach Earth. It's not because they don't exist. They probably do. It's not because they don't want to. They could be just as curious as we are. It's because physics doesn't allow it. The distances are too great. The energy requirements are too massive. The rocket equation is too tyrannical. The time required is too long. The dangers are too severe. The speed limit is too absolute. And the shortcuts, wormholes, warp drives are science fiction. Not science. They require physics that probably doesn't exist. So we're stuck in our solar system for now. Maybe someday, with incredibly advanced technology, we could send probes to nearby stars, maybe even colonize over millennia. But meaningful contact with distant civilizations, conversation, cultural exchange, cooperation, it's almost impossible because even radio signals take years, decades, centuries to travel and return. So we live in the prison. We all do. Every civilization throughout the universe, separated by the incomprehensible void. But maybe that's okay. Maybe we don't need physical contact to not be alone. Maybe just knowing that others exist somewhere, looking at their stars, wondering, is enough. And maybe the prison isn't so bad. We have our planet, our solar system, resources, space, time to grow, explore, evolve. And maybe in centuries, we will colonize Mars, Jupiter's moons, the asteroids. We will become an interplanetary civilization, if not interstellar. And maybe in millennia, we will send probes to Alpha Centauri, to Barnard's star, exploring, learning, expanding, slowly, patiently. Because even though we are trapped, we are not immobile. We can move within our prison. We can grow. We can reach. And perhaps that is enough. Perhaps we do not need to escape. We just need to continue. Exploring, questioning, being curious, being human. Good night. Rest well. And dream not of aliens visiting us, but of us, reaching for the stars, slowly, patiently, inexorably. Because even though physics limits us, it doesn't stop us, not completely. We are a species that looks up, that asks, what's out there? That builds spaceships, that sends probes, that refuses to stand still. And even if we never cross the galaxy, even if we never meet our cosmic neighbors, we can still explore, we can still discover, we can still reach within our prison, which is vast, beautiful, full of wonders, our solar system, our home, for now, and perhaps forever. But that's okay. because we are not alone in spirit. We know that others are out there, somewhere trapped in their own prisons, looking at their stars, wondering, just like us. And maybe, someday, our signals will cross in the void, not visitors but messages, saying, "We are here, we exist, you are not alone." And that will have to be enough, because physics says it must be. And physics always wins. Good night. Dream of the stars not as destinations, but as beacons, reminders that the universe is vast and beautiful and full of mystery, and that even though we are trapped, we are part of it, stardust, conscious, wondering, reaching, always reaching, towards the unreachable, because that is what it means to be human. Good night, and welcome to the prison. It is immense, it is beautiful, it is all we have, and it is enough. Good night.